Tonight, we're going to talk about something that's happening beneath your feet right now. Earth is spinning faster. Not by an amount you could feel in your morning routine, but by enough that the most precise instruments humanity has ever built are tracking it minute by minute. Days are getting shorter. Atomic clocks, the devices we use to define what a second even means, are drifting out of sync with the ground we stand on. And the changes run deeper than the surface, deeper than the crust itself, all the way down to a place no human has ever been. To an ocean of liquid iron churning in total darkness, 2,900 miles beneath your feet. By the end of tonight, you're going to understand what's happening to Earth right now, why it matters for every system we depend on, and what the geological record tells us about where this might be heading. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. On June 29th, 2022, something quietly historic happened. Earth completed one full rotation in less time than it ever had since scientists began measuring with atomic precision. The day was shorter than normal by 1.59 milliseconds. That sounds like nothing. A blink, a fraction so small it feels irrelevant. But when a planet, 4.5 billion years old, suddenly starts rushing through its own rotation cycle faster than any recorded point in modern history, scientists pay attention. This wasn't a one-time anomaly. 2020 set a record at the time. 2021 broke it. 2022 shattered it. Year after year, the planet has been logging some of the shortest days ever measured with modern instrumentation. And the forces responsible reach from the surface all the way to the very center of the planet. To understand what faster spinning actually means, you need to know something most people never think about. A day is not exactly 24 hours. It never has been. We measure a day as the time between one noon and the next, the duration from when the sun reaches its highest point in the sky until it reaches that same point again. And that duration changes. Not by amounts you'd notice in a lifetime, not even by amounts your grandparents would have noticed in theirs, but by fractions of milliseconds that add up over years and decades. For most of recorded history, those changes moved in one direction. The planet was slowing down. Tidal friction from the moon pulls at the oceans like a brake, dragging on the rotation millisecond by millisecond across millions of years. Ancient coral fossils tell us that 400 million years ago, a year had more than 400 days. The days were shorter because the planet was spinning faster. Over time, it slowed. That long, steady deceleration is the baseline, the expected direction of travel. Which is why what happened around 2016 stopped researchers cold. The trend reversed. Earth started speeding up, not dramatically, not in a way you would feel, but measurably, consistently. Here is what makes this strange. Beyond just the numbers, the forces that cause gradual slowing have not disappeared. The moon is still pulling. Tidal friction is still operating. Something else is now pushing in the opposite direction, hard enough to overcome it. That is the puzzle. And the candidates responsible reach from the surface of the planet all the way to its core. At the surface, melting ice is redistributing mass across the globe in ways that physically alter the spin. In the atmosphere, shifting pressure systems push against the rotating crust. In the oceans, changing current patterns apply their own subtle drag and release. And deep underground, A churning ocean of liquid iron more than 2,000 miles below your feet moves in ways that couple directly to the rotation of everything above it. Each of these forces is confirmed. Each is measurable. What scientists are still working out is how they interact, which one is dominant right now, and whether the acceleration is building towards something or approaching a reversal. What we know for certain is this: the planet is not behaving the way the models expected. The systems built to track time, synchronize satellites, and coordinate global infrastructure were designed around a slower Earth. They are now running behind, and the gap between atomic time and Earth time is forcing a decision that could crash the internet. That story starts with a single invention designed to fix a problem nobody saw coming. A millisecond feels meaningless. You cannot feel it. You cannot see it. If someone stole 1 millisecond from your day, you would never notice. But Earth is not a person. Earth is a system of systems, all synchronized to one another by the rhythm of rotation. And when that rhythm changes, even by a fraction of a millisecond per day, the ripple moves through every layer of that system. Here's what makes this matter. Every GPS satellite orbiting Earth right now was designed with an assumption built into its core programming. The assumption is that Earth rotates at a predictable rate, that the surface beneath the satellite moves through space at a speed that changes slowly, gradually, in ways that can be calculated years in advance. The same assumption lives inside every power grid, every financial trading system, every air traffic control network. They were all built for a planet that behaves within a specific range. When the planet steps outside that range, even by milliseconds, the synchronization starts to slip. The longer the mismatch runs, the further everything drifts from the timing it was calibrated around. And the systems most vulnerable to that drift are the ones that tie our entire digital infrastructure together. Global Positioning System satellites orbit at a specific altitude and broadcast signals timed to nanosecond precision. They are synchronized to atomic time, which is anchored to the behavior of cesium atoms, not to the planet's spin. When Earth turns slightly faster, the planet's surface moves ahead of where the satellites expect it to be. The position data shifts, not by miles, not even by feet, by centimeters. But in aviation, navigation, surgical robotics, and autonomous vehicle systems, centimeters matter. Financial systems are another layer of this. Stock exchanges in New York, London, Tokyo, and Frankfurt execute millions of trades per second. Each transaction carries a timestamp accurate to the microsecond. Those timestamps are synchronized to coordinated universal time, which is itself anchored to atomic clocks. A desynchronized planet creates a desynchronized timestamp, and in high-frequency trading, even a microsecond of ambiguity can represent millions of dollars of exposure. Power grids are perhaps the most physical example. Alternating current flows at a fixed frequency, either 50 or 60 cycles per second, depending on the country. Grid operators synchronize their systems to universal time to balance load across regions. When time drifts, load balancing drifts with it. Now, here is the layer most people do not consider. All of this was already accounted for. Scientists knew Earth's rotation was imperfect. That is why the leap second was invented in 1972. Periodically, 1 extra second would be added to the official clock to keep atomic time aligned with Earth time. It was a patch, a small correction applied whenever the gap grew too large. 27 leap seconds have been added since the system began. Not 1, has ever been removed. The planet was always slowing, which meant atomic clocks always ran ahead, which meant the fix was always to add time. Now, the planet is speeding up. Atomic clocks are falling behind. And, for the first time in the history of the system, the discussion has shifted to removing a second from the official clock rather than adding one. That is called a negative leap second. And the engineers responsible for internet infrastructure have described it on record as one of the most dangerous things that could happen to global digital systems. 1 second backward. The consequences of that single subtraction are stranger and more serious than almost anyone outside the field realizes. But before we get there, we need to understand the instrument that caught this acceleration in the first place. Because what atomic clocks actually are and how they detected the planet speeding up is a story that begins inside a single vibrating atom. Before 1955, the most accurate clocks on Earth lost or gained about 1 second every 300 years. That sounds precise. By the standards of daily life, it was extraordinary. By the standards of planetary science, it was nowhere near good enough. Then, physicists built the first atomic clock. The principle is this: atoms do not lie. Every atom of the same element anywhere in the universe vibrates at exactly the same frequency. Cesium, 133 atoms, the type used in the most precise atomic clocks, oscillate 9,192,631,770 times per second, every single time, without exception, without drift. That frequency became the new definition of a second, not a fraction of Earth's orbit, not a pendulum swing. The vibration of a single type of atom counted 9 billion times over. The result was a clock so accurate it would not gain or lose a single second across 300 million years. With that level of precision suddenly available, scientists could do something they had never done before. They could measure the planet. And what they found was unsettling from the beginning. Earth's rotation, it turned out, was messy. It fluctuated constantly. The planet sped up slightly in winter in the northern hemisphere, as atmospheric mass shifted toward the poles. It slowed slightly in summer. Earthquakes made tiny adjustments. Major storms applied measurable pressure, El Niño events, shifts in ocean circulation, even large amounts of snow accumulating at high latitudes, all left faint signatures in the rotation data. Researchers were measuring these variations and accounting for them. The system worked. The leap second kept atomic time and Earth time from drifting too far apart. Everything was manageable. Then came the data. From 2016 onward, the fluctuations were still there, but underneath them, a clear signal was emerging. The average length of a day was shrinking. Not randomly, not as a seasonal variation that would correct itself, as a trend. Year after year, the averages were falling in one direction. The first response in the scientific community was exactly what you would expect. Check the instruments. Rule out calibration errors. Cross-reference data from atomic clock networks in different countries on different continents. The International Earth Rotation and Reference System Service, the organization that monitors this globally, ran the checks. The instruments were fine. The signal was real. Here is the detail that stopped researchers mid-sentence in the papers. The acceleration was not explained by any single known mechanism. Tidal friction was still operating as expected. Seasonal atmospheric shifts were accounted for. When scientists subtracted every known contributing factor from the data, a residual acceleration remained. Something beyond the catalogued causes was pushing the planet forward. They had a measurement without a complete explanation. That situation in science is where things get interesting and occasionally alarming. Because the deeper researchers dug into what might explain the leftover signal, the more they found themselves looking not at the surface of the planet, not at the ice or the atmosphere or the oceans, but straight down, 2,900 miles down, into a place no instrument has ever physically reached, where iron flows like a slow ocean, in total darkness, under pressure that would crush any known material to powder. In 1972, the world quietly agreed on a fix to a problem most people did not know existed. Atomic clocks were now the gold standard for time. They were anchored to physics, not to the planet. And the planet, as it turned out, was an unreliable timekeeper. Its rotation fluctuated. It was gradually slowing down due to tidal drag from the moon. And if nothing was done, atomic time and Earth time would drift further and further apart with every passing decade. That mattered because nearly all human systems were built around the assumption that noon meant the point when the sun sat highest in the sky. If clocks kept perfect atomic time while the planet slowed, eventually noon on the clock would arrive while the sky still showed late morning. Not tomorrow, not next year, but across centuries, the drift would become undeniable. The solution was the leap second. Once or twice a year, when the gap between atomic time and Earth time grew large enough, international timekeeping authorities would add a single extra second to the official clock. Clocks around the world would tick from 23 hours 59 minutes 59 seconds to 23 hours 59 minutes 60 seconds before rolling over to midnight. One extra heartbeat inserted into global time. It sounds elegant. In practice, it was always awkward. Computer systems are not designed for a minute that contains 61 seconds. Operating systems, databases, and network servers all have to handle that extra second in their own way, and they do not always agree on how. In 2012, a leap second crashed servers at Reddit, LinkedIn, Qantas Airlines, and hundreds of other organizations simultaneously. Engineers spent hours diagnosing what turned out to be a single added second, interacting poorly with certain software scheduling systems. And that was a positive leap second, time moving forward, adding something. Nobody had ever had to subtract one. Here is the technical reality of a negative leap second. Clocks would tick from 23 hours 59 minutes 58 seconds directly to midnight. 23 hours 59 minutes 59 seconds would simply not exist. Every system expecting that second, every log file, every transaction, every scheduled process timed to that moment would encounter a gap, a hole in time. Engineers at Meta, the company that operates Facebook and Instagram, published a paper describing the potential consequences. They called the negative leap second an event with a devastating effect on software relying on timers or schedulers. Their recommendation was not to apply one at all, but instead to smear the correction across a longer period, spreading the adjustment over hours rather than applying it in a single jump. The problem is that smearing creates its own inconsistencies. Different systems smear differently. And during the transition period, two systems comparing timestamps would be operating in subtly different versions of time. In 2022, an international standards body voted to eliminate the leap second entirely by 2035, allowing atomic time and Earth time to drift without correction until the gap is handled through a different mechanism entirely. That decision may sound like a clean solution. It is not. It simply defers the problem by allowing a gap to grow instead of patching it in real time. And the gap is currently growing in a direction nobody planned for. Because as Earth keeps accelerating, that gap compounds. And the systems most vulnerable to it are not old infrastructure or outdated software. They are the satellites positioning every aircraft, ship, and self-driving vehicle on Earth. Think about what a negative leap second actually means. Every computer system on Earth expects time to move in one direction, forward, in discrete steps from 1 second to the next. Operating systems count those seconds. Databases timestamp every transaction by those seconds. Networks synchronize by comparing those seconds across thousands of servers. The entire architecture of digital infrastructure assumes that if you're at second 59, the next moment will be second 60. Then the clock rolls to 0 and starts a new minute. A negative leap second breaks that assumption. The clock jumps from second 58 directly to 0. Second 59. Never happens. Every system expecting that second, every log file, every transaction, every scheduled process timed to that moment encounters a gap, a hole in time where something should be but isn't. The Internet runs on a protocol called the Network Time Protocol, which constantly synchronizes clocks across billions of devices. It was designed to handle time moving forward. It was never designed to handle time moving backward. When a system's internal clock suddenly reads 1 second earlier than it did a moment ago, processes that were scheduled to run at a specific timestamp can trigger twice. Logs that record events in chronological order can record new events as if they happened before old ones. Security certificates that verify identity using timestamp matching can fail. In financial markets, the damage is easier to quantify. High-frequency trading systems execute thousands of transactions per second. Order books match buyers to sellers based on the precise sequence of submitted orders. If one exchange's clock jumps backward while another's does not, the sequence of trades becomes ambiguous. Transactions that appeared settled become disputed. Trades placed after the subtracted second might be logged as occurring before trades placed before it. Power grid operators face a different version of the same problem. Grid synchronization relies on timestamps to balance electricity loads between regions. A sudden discontinuity in time creates a window where the coordination signal breaks down. In most cases, backup systems compensate quickly. But the industry has a term for what happens in the gap, a synchronization event. And synchronization events, even brief ones, are the precursor to the kind of cascading failures that bring down large sections of a grid. Aviation adds another layer. Air traffic control systems depend on synchronized timestamps to track aircraft positions and resolve conflicts between flight paths. When controllers at different facilities are working from clocks that disagree, even briefly, the margin built into separation standards gets consumed by the ambiguity. Meta's engineering team estimated the risk was significant enough to argue publicly against ever applying a negative leap second. Google, Amazon, and Microsoft have all developed their own time smearing approaches as a workaround. None of these companies came to the same solution. Which means, in the event of a negative leap second, the largest technology organizations on Earth would be running slightly different versions of time simultaneously. The standards bodies chose to eliminate the leap second going forward rather than face this scenario. But the underlying problem A planet rotating faster than the timekeeping infrastructure was designed for does not disappear with a policy decision. It just keeps compounding. And the engineers who maintain these systems know something most people don't. The force driving that acceleration is not coming from the surface. It is not the ice. It is not the atmosphere. The deepest signal in the data points somewhere far more difficult to observe, somewhere no human has ever been, and no instrument has ever survived reaching. Every time you use navigation on your phone, a quiet negotiation happens between your device and a constellation of satellites orbiting more than 12,000 miles above the surface. Those satellites do one thing. They broadcast a timestamp. Your device receives signals from at least 4 of them, compares the tiny differences in when each signal arrives, and uses those differences to calculate exactly where on Earth you are. The whole system depends on one assumption, that the satellites know where Earth is, not in a vague sense, not approximately, to within centimeters. Each global positioning system satellite carries multiple atomic clocks and orbits on a precisely calculated path. Ground stations track those orbits continuously and send correction data to keep the satellite's position model accurate. The satellites, in turn, know where the surface of Earth should be at any given microsecond based on the planet's expected rotation rate. When Earth rotates faster than expected, the surface moves ahead of the prediction. The error is small. Depending on the degree of mismatch, it might translate to a positional error of a few centimeters to a few meters. For a family using navigation to find a restaurant, that is irrelevant. For a cargo ship navigating a narrow strait at night, it is the difference between a clean passage and a grounding. For a precision-guided aerial system or a surveying instrument building a tunnel from both ends simultaneously, it is not acceptable at all. Ground control teams correct for Earth's rotation variations constantly. It is not a new problem, and the systems have margins built in, but the corrections are applied in updates, not continuously. Between updates, the system operates on its last known model of Earth's behavior. When the planet accelerates in an unexpected way, those updates lag behind the reality. There is a deeper issue that does not get discussed in consumer technology coverage. The global positioning system was not built alone. Russia operates GLONASS. The European Union operates Galileo. China operates Beidou. Each of these systems uses its own set of atomic clocks and its own set of ground correction stations. They are all coordinated to the same underlying time standard, but they do not update simultaneously, and their correction models do not always agree. When Earth behaves normally, the disagreements between systems are negligible. Position fixes from different constellations produce essentially identical results. When Earth accelerates in a way that pushes against the correction models, the disagreements widen. And the devices that blend signals from multiple constellations to improve accuracy can begin receiving contradictory position data. Aviation relies on blended positioning more than almost any other industry. Modern instrument approaches at airports use satellite positioning to guide aircraft to within feet of a runway in zero visibility. The tolerances are extraordinarily tight. The safety margins are real, but not unlimited. This is why agencies responsible for satellite navigation issue what are called notices to air missions whenever unusual behavior is detected in timing systems. They are not rare. Several have been issued in recent years specifically related to timing anomalies. The point is not that the sky is falling. The systems are robust, and the engineers maintaining them are skilled. The point is that those engineers are working harder than they were a decade ago to keep a planet-scale timing mismatch from propagating into systems that people's lives depend on. And the harder question is why the planet accelerated in the first place. The atmosphere plays a role. The oceans play a role. The ice plays a role. But underneath all of it, there is a force so deep and so strange that understanding it requires picturing something almost impossible to imagine. An ocean of liquid iron, 2,900 miles beneath your feet, moving in the dark. If you could drill straight down through the crust, through miles of rock, through the upper mantle, through the lower mantle, and keep going past the point where the pressure becomes so extreme that atoms themselves are forced into configurations that do not exist at the surface, you would eventually reach the outer core. It begins roughly 1,800 miles down and extends another 1,400 miles further in. It is composed primarily of iron and nickel. It is hotter than the surface of the sun. And it is entirely liquid. Not liquid like water, liquid like metal that is so compressed, so energized that it flows in massive currents driven by the temperature difference between the relatively cooler base of the mantle above and the intense heat of the solid inner core below. Those currents are not slow. On geological timescales, they move with surprising speed, tens of miles per year, and they carry electrical charge. Flowing liquid iron generates a magnetic field through a process called the geodynamo. The currents create electrical currents. The electrical currents create magnetism. And that magnetism extends outward, from the core, through the mantle, through the crust, and out into space, forming the protective bubble that deflects charged particles streaming from the sun. Without it, those particles would strip away the atmosphere and scour the surface. The liquid outer core is, in a very direct sense, why Earth is livable. But it does more than generate the magnetic field. It physically interacts with the rotation of everything above it. Here is where it connects to the speed anomaly. The outer core does not rotate at exactly the same rate as the mantle and crust above it. There is a slight coupling between them, transmitted through pressure and electromagnetic forces, but the core has some rotational independence. When the currents inside it shift, when massive columns of rising and sinking iron change their flow patterns, they exert torque on the layer above them. That torque is measurable in the rotation data. Researchers, studying the correlation between changes in Earth's magnetic field and changes in rotation rate, have found a pattern. When the field fluctuates in certain ways, the rotation tends to change. The connection is not perfectly understood, and the mechanisms are still being debated. But the correlation is strong enough that geophysicists now treat core dynamics as a primary driver of decade-scale rotation variations. The acceleration that began around 2016 coincides with changes in the outer core's circulation pattern detected in satellite magnetic data. The timing is not a coincidence. And here is what makes it stranger. The outer core does not move in isolation. It wraps around something at the very center of the planet, something solid, something that has its own rotation rate, its own angular momentum, and its own relationship with the layers above and below it. The inner core, a ball of solid iron roughly the size of the moon, turning inside the liquid iron ocean, inside the mantle, inside the crust, inside the layer of water and rock and air where you live. And in recent years, researchers discovered that this innermost sphere had been doing something nobody expected. It slowed down. And then, possibly, it stopped. And then, according to the most recent data, it may have started turning in the other direction. At the very center of Earth, about 3,200 miles beneath your feet. There is a sphere of solid iron, roughly as wide as the moon. It exists in a state that should not be possible by ordinary standards. The pressure at that depth is more than 3 million times the atmospheric pressure at the surface. The temperature is roughly 9,000 degrees Fahrenheit, comparable to the outer layer of the sun. At that temperature, iron should be liquid. At that temperature, nearly everything should be liquid. It is not liquid, it is solid. And it is solid precisely because of the pressure. The weight of the entire planet, pressing inward, forces the iron into a crystalline structure so tightly packed that heat cannot shake it apart. The inner core sits suspended in the liquid outer core with no physical connection to anything above it. No rigid structure holds it in place. No tether ties it to the mantle or the crust. The only forces acting on it are gravity, pulling it toward the center, and the pressure and electromagnetic fields from the liquid iron surrounding it. This means the inner core can rotate at its own rate, independent of everything above. For decades, geophysicists suspected it did. The evidence came from an unusual source: earthquakes. When a major earthquake strikes, it sends seismic waves radiating outward in all directions, including straight down through the core and up the other side. Researchers at seismograph stations positioned strategically around the globe record those waves and use the travel times to map the interior. Different materials transmit seismic waves at different speeds, and the inner core, with its iron crystal structure aligned in a particular orientation, transmits waves slightly faster along certain paths than others. By comparing seismic recordings of similar earthquakes over decades, scientists found that the travel times were changing. Waves that passed through the inner core were arriving at slightly different times in recent decades than they had earlier. The best explanation was that the inner core was rotating faster than the mantle above it, slowly turning relative to the surface, changing the orientation of its crystal structure relative to the paths the waves were traveling. In 2023, a study published in the journal Nature Geoscience drew a different conclusion from a longer data set. The inner core had been rotating faster than the surface through the 1990s. Sometime around 2009, it slowed to match the surface. Around 2010 to 2012, it appeared to slow further, rotating slightly slower than the mantle above it. The conclusion the researchers reached was this: the inner core had reversed its rotation relative to the surface. It was now turning fractionally in the opposite direction from the planets surrounding it. That is a sentence that requires a moment to sit with. The solid iron center of Earth, 360 degrees turn, after 360 degrees turn, is now spinning opposite to the planet you live on. The forces involved are enormous. The angular momentum of the inner core is not a small quantity. Its changes in rotation couple to the outer core, which couples to the mantle, which couples to the crust. Each coupling is imperfect. Each one introduces a delay, a torque, a transfer of rotational energy that propagates upward through the layers. Some researchers believe the inner core's reversal is directly linked to the surface acceleration. The mechanism is still being worked out. The data is still being debated. But something at the center of this planet changed its behavior, and the effects are still traveling upward. The discovery that Earth's inner core may have reversed its rotation relative to the surface is one of the most significant findings in deep Earth science in decades. It is also one of the most contested. Let's establish what is agreed upon before reaching the edges of the debate. Seismic data, covering roughly 60 years, shows a clear pattern. The inner core was rotating slightly faster than the mantle and crust through the late 20th century. Multiple independent research teams, using different data sets and different methods, confirmed this over-rotation. It was not controversial. It was consistent with models of how the core behaves under the electromagnetic forces from the outer core and the gravitational influences from the mantle. What happened next is where the science gets complicated. The over-rotation appears to have slowed. By some measurements, it stopped entirely around 2009 or 2010. The question the community is now arguing over is whether the inner core is currently in a static phase, matching the rotation of the mantle above it, or whether it has continued its deceleration past zero and is now rotating in the opposite direction relative to the surface. The evidence for reversal comes primarily from the 2023 Nature Geoscience study by Yang and Song, which examined repeating earthquake sequences recorded at the same seismograph stations over multiple decades. Their analysis suggested the inner core's seismic signature had flipped in a way consistent with reversed rotation. Critics of the study, and there are credible ones, argue that alternative explanations exist. The inner core's surface is not perfectly smooth. It has topographic features, valleys and ridges of iron crystal that could scatter seismic waves differently over time without requiring rotation. Changes in the structure of the outer core above could also affect wave travel times. What both sides agree on is this: something changed inside the planet. The inner core's behavior in the 21st century is different from its behavior in the 20th century. And when the core changes its rotational behavior, it does not happen silently. The mechanism connecting core rotation to surface rotation runs through angular momentum conservation. When the inner core decelerates, that angular momentum does not disappear. It transfers through electromagnetic and gravitational coupling to the outer core. The outer core transfers it to the mantle. The mantle transfers it to the crust. Angular momentum moving upward. Through those layers is angular momentum being added to the rotation of the surface. The inner core slows down, and the surface speeds up. Not instantly, not in a single dramatic shift, but gradually, as the rotational energy propagates upward through each layer, coupling imperfectly at each boundary, taking years to decades to fully express itself at the surface. The timeline fits. The inner core's apparent deceleration in the late 2000s and early 2010s aligns, with a lag appropriate to the transfer timescales, with the surface acceleration that became measurable starting around 2016. That lag is itself scientifically interesting. It suggests the coupling is not instantaneous, that information from the center takes years to decades to propagate upward through the layers, which raises a question that nobody has a clean answer to yet. If the inner core reversal is real and continuing, what happens next? What does the surface look like at the far end of this angular momentum transfer? The answer might be written in the ice. Because while the core drives things from the inside, the surface of the planet is also being reshaped by something happening at the poles. Something that is accelerating faster than most models predicted 10 years ago. The physics here is simple, even if the implications are not. Angular momentum is conserved. That's not a theory or a model. It's one of the fundamental laws that governs how rotating objects behave anywhere in the universe. If you have a spinning object and you move mass closer to the center of rotation, the object spins faster. If you move mass away from the center, it slows down. The total angular momentum, the product of how fast something spins and how its mass is distributed, stays constant. Earth is a spinning object. Ice sheets sitting near the poles are mass-positioned close to the rotation axis. For most of the last 20,000 years, massive ice sheets covered large portions of the planet's surface, concentrated primarily near the poles. Ice near the poles sits close to Earth's rotation axis. When that ice melts and the water flows into the oceans, it redistributes away from the poles and spreads across lower latitudes, moving mass away from the rotation axis. Pulling mass away from the axis should slow the rotation. And for most of the Holocene, that slow post-glacial rebound effect has been doing exactly that, contributing to the long-term deceleration of Earth's spin. But something has changed in the rate. The Greenland ice sheet and the West Antarctic ice sheet are losing mass at rates that have accelerated sharply since the 1990s. Greenland alone is now losing roughly 280 billion metric tons of ice per year. Antarctica is losing roughly 150 billion metric tons per year. Those numbers are large enough to detect from space. The Gravity Recovery and Climate Experiment satellites, known as GRACE, and its successor, GRACE Follow-On, measure tiny variations in Earth's gravitational field by tracking the distance between two satellites flying in formation. When mass shifts on the surface, the gravitational field shifts with it, and the satellites drift closer together or further apart by a fraction of a micrometer. Using that data, scientists have directly mapped the redistribution of mass as ice melts. The picture is striking. The poles are losing mass. The mid-latitude ocean basins are gaining it. Earth's moment of inertia, the rotational equivalent of mass distribution, is shifting in real time in a direction that the physics says should slow the rotation, and in the long run, it will. Post-glacial rebound, the slow rising of land that was compressed under ancient ice, will continue to pull mass toward the poles for thousands of years, gradually acting as a brake. But here is the short-term complication. The redistribution is not uniform. Different parts of the ice sheets melt at different rates. Different ocean basins accumulate water at different depths and latitudes. The interaction between where mass is going and how that interacts with Earth's three-dimensional shape produces effects that are not simply the sum of their parts. And one of those effects is that the planet's rotation axis is physically moving. Not the magnetic pole, the actual spin axis, the imaginary line through the planet around which everything rotates. It has shifted by measurable amounts in the last 20 years in a direction that aligns with the observed ice loss pattern. This is confirmed by satellite data. It is not a model prediction. It is a measurement. And the implications of a shifting rotation axis reach into everything from sea level projections to the long-term behavior of the magnetic field. But before we get there is something else in the rotation data. Something quieter, slower, and harder to explain. A wobble that went mysteriously still. Earth does not spin on a perfectly stable axis. It wobbles. It has always wobbled. Multiple overlapping wobbles, each with its own period and cause, combine into a complex drift of the geographic poles that scientists have been tracking with increasing precision since the late 19th century. The one that concerns us here is called the polar drift, the gradual, irregular movement of the geographic North Pole across the Arctic surface. For most of the 20th century, the North Pole drifted slowly in one direction toward northern Canada at a rate of a few centimeters per year. The cause was primarily post-glacial rebound, the continuing adjustment of the crust and mantle to the removal of the massive ice sheets that covered North America and northern Europe during the last ice age. Then, around the year 2000, the direction of polar drift changed. It turned eastward toward Greenland. The rate increased substantially, from a few centimeters per year to roughly 17 centimeters per year over the course of the 2000s and 2010s. When researchers analyzed the cause of the directional shift, the answer came back clearly from the GRACE satellite data. The primary driver was ice loss from Greenland. Greenland sits in a specific location relative to the polar drift trajectory. As its ice sheet loses mass, it changes the distribution of planetary mass in a way that pulls the pole in a new direction. The correspondence between the onset of accelerated Greenland ice loss and the shift in polar drift direction is close enough that scientists treat them as directly linked. Western Antarctic ice loss has also contributed, pulling the axis in a slightly different direction and adding to the net eastward trend. The result is that the actual geographic pole, the point on the surface directly above Earth's rotation axis, is now located somewhere measurably different from where it was when you were born. This is not a dramatic shift in the planet's orientation. It is not something that would change where you see the North Star from your backyard, at least not on any human timescale. But at the precision required by satellite systems, geodetic surveys, and time transfer infrastructure, it matters. Every system that uses the precise location of Earth's rotation axis in its calculations has to be updated to account for the drift. The International Earth Rotation and Reference System Service publishes updated Earth orientation parameters regularly, and those parameters feed directly into the correction models used by satellite navigation systems globally. The updates have been coming faster in recent years, and the rate of ice loss is not slowing, it is accelerating. Models from the early 2000s underestimated how quickly the ice sheets would respond to warming. The actual data has outpaced several generations of projections. If the ice loss rate continues to increase, the polar drift will also continue to accelerate. The axis will move faster. The corrections will need to be applied more frequently and across a wider range of systems. And there is a second-order effect that is more difficult to calculate. The mass redistribution from ice loss changes the planet's moment of inertia in a way that interacts with the other wobbles. It does not just shift the axis. It changes how the planet responds to other forces acting on it. One of those responses is a slow rhythmic rocking called the Chandler wobble. It has been one of the most reliable features of Earth's rotational behavior for as long as it has been measured. In the early 2000s, it nearly stopped. The water that was once frozen in Greenland and Antarctica does not simply disappear when it melts. It enters the ocean system. And the ocean is not a uniform container. It has basins, ridges, and trenches of different depths. It is subject to different temperature and salinity gradients at different latitudes. And the planet's rotation, the same rotation we are tracking through all of this, influences how water distributes itself across those basins. The result is that sea level rise is not uniform. This surprises most people when they first encounter it. The intuition is that water fills a bowl evenly, but the ocean is not a bowl. It is a rotating three-dimensional fluid system wrapped around an irregularly shaped mass with uneven internal density. Near a large ice sheet, sea level actually drops when the ice melts. The ice sheet is so massive that its gravitational attraction pulls ocean water toward it. When the ice disappears, that gravitational attraction weakens, and the water that was pulled toward the poles sloshes outward toward lower latitudes. Coastlines near Greenland experience a small sea level drop as Greenland loses ice. Coastlines in the tropics and the southern hemisphere experience disproportionately large rises. The redistribution also affects the planet's rotational response. Adding mass to lower latitude ocean basins increases the distance of that mass from the rotation axis. An increased moment of inertia, with angular momentum conserved, means a slower rotation. In the long term, as more ice melts and more water moves toward lower latitudes, this effect should produce a measurable deceleration. But we are not in the long term. We are in the transition. During the transition, the redistribution is happening simultaneously in multiple regions at different rates with different rotational signatures. Greenland melts faster in summer. Antarctic glaciers carve ice throughout the year. Monsoons and El Niño cycles move water between basins seasonally. The net rotational effect at any given moment is the sum of all those contributions, and it oscillates even as its long-term average moves in one direction. This oscillation makes the short-term picture difficult to separate from background noise. It is one reason why researchers cannot yet point to a single cause for the recent surface acceleration and say, this is it. The ice contribution, the core contribution, the atmospheric contribution, and the ocean contribution are all real. Separating them requires extremely precise measurement over decades. What researchers can say with confidence is this: the ocean mass redistribution is measurable from space. It is changing the planet's moment of inertia in real time. And the rate at which it is changing is faster than models predicted 2 decades ago. The planet is not just spinning faster, its weight is shifting. And when the weight of a spinning object shifts, it does not just change speed, it changes the way it wobbles. Earth's wobble has a cycle, a roughly 14-month cycle that should be rock steady, driven by the geometry of the planet itself. For decades, it was. Then it slowed. Then it quieted. Then, in the early 2000s, for reasons that are still not fully explained, the wobble, that should have been perfectly predictable, became irregular, and some of the data suggests it nearly stopped altogether. Earth wobbles as it spins. Not in a catastrophic sense, not in a way that would shift the seasons or tilt mountains, but in a slow, cyclical rocking of the rotation axis relative to the solid body of the planet, repeating roughly every 14 months. This is called the Chandler wobble, named after the American astronomer Seth Carlo Chandler, who documented it in the 1890s. The cause of the wobble is geometry. Earth is not a perfect sphere. It is slightly flattened at the poles and bulging at the equator. A non-spherical rotating object does not spin in perfect alignment with its geometric axis. It wobbles around it, the way a football tumbles slightly as it spirals through the air. For a rigid body, this wobble should damp out over time due to friction. Earth is not perfectly rigid. The crust flexes. The mantle flows slowly. The oceans slosh. These flexibilities continuously re-excite the wobble, keeping it going even as dissipation works against it. The Chandler wobble traces a small circle roughly 30 feet across at the pole that repeats on its 14-month cycle. Superimposed on it is an annual wobble caused by seasonal shifts in atmospheric mass and ocean loading. The combination of the two produces a beat frequency that traces a slightly irregular ellipse over periods of about 6 years. It has been one of the most predictable features of Earth's rotational behavior. Then, around the year 2000, it started behaving differently. The amplitude of the wobble, how large the circle traced by the pole was, began to decrease. By around 2005 to 2006, the Chandler wobble had dropped to roughly 1/5 of its typical amplitude. It had nearly vanished. This was noticed. Papers were published. The scientific community debated what could cause such a suppression. The leading hypothesis pointed to a redistribution of ocean bottom pressure. Deep ocean currents, specifically changes in where cold, dense water sinks to the ocean floor, had shifted in a way that damped the excitation, keeping the wobble going. Ocean temperature changes associated with a prolonged La Niña cycle were identified as a likely contributor. The wobble eventually recovered. By the late 2010s, it was operating closer to its normal amplitude again. But the episode raised something that researchers found uncomfortable. A force as fundamental as the Chandler wobble, operating for as long as Earth has had its current shape, had been significantly suppressed by changes in ocean circulation. If ocean changes could do that, other changes could suppress or amplify other fundamental rotational features. And if the ice redistribution continues at its current rate, if the ocean circulation patterns continue to shift, and if the core dynamics described in earlier chapters continue to evolve, the combination of effects on Earth's rotation could take the system outside any behavior observed in the modern instrumental record. At that point, the only reference left would be the deep past, ancient rocks, coral skeletons, the geological record of how Earth behaved the last time conditions were similar. And there is another layer in the present-day picture that has not been discussed yet. A region of the planet where the magnetic field has already weakened by more than 20% compared to its typical strength. A region sitting directly over South America and the South Atlantic Ocean. A region that, based on current trends, may be splitting into two. Earth's magnetic field is not uniform. It does not wrap the planet evenly, like a symmetrical shell. It is generated by the turbulent asymmetric flow of liquid iron in the outer core, and the result is a field with regional variations, stronger in some areas and weaker in others, shifting in strength and location over decades and centuries. Most of those variations are minor, but one region stands out and has been standing out with increasing intensity for the last century. The South Atlantic anomaly is a large region centered roughly over the South Atlantic Ocean and extending across much of South America, where the magnetic field is significantly weaker than the global average. In the strongest part of the anomaly, the field is roughly 40% weaker than it would be at equivalent latitudes in other parts of the world. That weakness has a consequence at altitude. Earth's magnetic field deflects charged particles from the Sun, the protons and electrons that stream outward in what is called the solar wind, as well as higher energy cosmic rays from beyond the solar system. In most places, this protection begins at a sufficient altitude that satellites in low Earth orbit are shielded. In the South Atlantic anomaly, the field is so weak at lower altitudes that charged particles penetrate further before being deflected. Satellites passing through this region encounter elevated radiation levels that can cause electronic malfunctions. The International Space Station takes extra precautions when its orbit carries it through the anomaly. Astronauts are warned. Sensitive instruments are powered down or protected. This is not a new phenomenon. The anomaly has been documented since the 1950s. What is new is that it is growing. The anomaly is expanding in area and deepening in its minimum intensity. It is also showing signs of developing a second minimum, a split into two separate weak spots, which researchers have found evidence for in the current field data. The cause is tied directly to what is happening in the outer core beneath that region. Under the South Atlantic, there is an unusual structure in the outer core called a low-velocity zone, where liquid iron moves differently from the surrounding material. Some researchers believe this zone represents a patch of reversed magnetic polarity, where the local field alignment is opposite to the global dominant direction. The interaction between this reversed patch and the overall field above it produces the surface weakness. The reversed patch is not static, it is growing. And this connects back to the rotation story in a way that is not immediately obvious. Changes in outer core flow patterns affect the magnetic field. Changes in the magnetic field affect the electromagnetic coupling between the outer core and the mantle. Changes in that coupling affect the transfer of angular momentum between the core and the surface. The South Atlantic anomaly is not just a radiation hazard for satellites. It is a visible symptom of changes happening in the outer core, the same outer core whose dynamics appear to be linked to the surface acceleration. The two phenomena are not the same thing, but they share an origin. And if the anomaly's low-velocity zone continues to grow, it will affect both the magnetic field above and the rotational coupling below. The last time Earth's magnetic field weakened significantly on a global scale, something more dramatic followed. The field reversed entirely. North became south. South became north. It has happened hundreds of times in Earth's history. And the current state of the field is making at least some researchers ask whether we are in the early stages of another one. Magnetic field reversals are one of the stranger confirmed facts in Earth science. The polarity of the planet's magnetic field has flipped roughly every 200,000 to 300,000 years on average, though the timing is highly irregular. The last full reversal, called the Brunhes-Matuyama reversal, occurred roughly 780,000 years ago, which means, by average statistics alone, we are overdue. That statement requires immediate context. The word overdue does not carry the same meaning here as it does for a dental appointment. The timing of reversals is not clockwork. The gap between reversals ranges from tens of thousands to tens of millions of years. Being past the average interval tells us almost nothing about when the next one will occur. What it does tell us is that reversal is a normal part of Earth's behavior. It has happened hundreds of times. Life has survived every one of them, but survived is doing some work in that sentence. During a reversal, the field does not simply flip instantaneously. The transition takes thousands of years. During that transition, the field weakens significantly, potentially dropping to 10 to 20% of its normal strength globally. The protection against charged particles from above is reduced across most of the planet. The consequences are not extinction level, but they are not trivial either. Increased radiation reaching the surface would elevate cancer rates. It would intensify damage to satellites and power grid infrastructure. It would affect animal navigation systems that depend on magnetic sensing, including migratory birds, sea turtles, and certain fish species. The atmospheric chemistry could be affected by the increased particle flux. Here is the connection to rotation that closes the loop. The geodynamo that generates the magnetic field is powered by the same convective flows in the outer core that interact with the rotation of the planet. The field and the rotation are not independent systems. They are coupled. When the outer core's flow patterns change in ways that weaken the field, those same changes alter the electromagnetic torque on the mantle above. That torque affects the rotation rate of the surface. Researchers studying paleomagnetic records, the preserved record of past magnetic field behavior in ancient rocks and seafloor sediments, have found correlations between periods of field weakness and anomalies in paleoclimatic and geological records. The relationships are not fully understood, but they are real enough to warrant continued investigation. What is particularly relevant to the present moment is this. The current rate of weakening is faster than the global average rate during non-reversal periods. The South Atlantic anomaly is the most visible regional symptom of that weakening, but global field intensity has declined by roughly 9% since measurements began in the early 19th century. 9% in roughly 180 years is a significant rate of change. Whether it represents the beginning of a reversal, an excursion, a temporary fluctuation that will correct itself, or something else entirely, is not yet determinable. What can be said is that the field is behaving differently today than it was 200 years ago, and the outer core driving it is behaving differently than it was 2 decades ago. And the surface is rotating faster than it has in 50 years. These are all real measurements. The question of how they connect and what their combined trajectory looks like over the next century is one that geophysicists are working urgently to answer. Part of that work involves reading the past. And the past is written in rock. There is a library inside the planet. Not books, not symbols, but physical records left in stone by the magnetic field of the past, pressed into cooling rock at the moment it solidified, never altered afterward. When lava erupts and cools into basalt, tiny magnetic minerals in the rock align themselves to the direction and intensity of Earth's magnetic field at that exact moment. They freeze in place as the rock hardens. The record they carry can survive for hundreds of millions of years without degradation. Using this method, paleomagnetists have mapped the history of Earth's magnetic field with remarkable detail, going back more than 4 billion years. But magnetic records are not the only information preserved in ancient rock. Thin layers in seafloor sediments record cyclic variations in sediment deposition tied to the number of days in a year. Tidal rhythmites, layers of sediment deposited by tides, preserve a count of tidal cycles per year, which is directly related to rotation rate. Ancient coral is perhaps the most famous of these recorders. Coral grows in daily and annual increments, and the growth rings can be counted much like tree rings. Corals from 400 million years ago, analyzed in the 1960s, showed approximately 400 growth rings per year. Since a year has a fixed length determined by the orbit around the Sun, more days per year means shorter days. Earth was spinning faster. Tidal rhythmites from approximately 620 million years ago suggest Earth had a day of roughly 21 to 22 hours. At that time, the planet has been slowing for hundreds of millions of years. The trend is real, and the direction is confirmed. But within that long deceleration, there are variations, periods where the rate of slowing changed, periods where small reversals of the trend occurred. The record shows that Earth's rotation is not a simple one-way street. It has fluctuated on timescales from decades to millions of years, driven by the interplay of tidal braking, core dynamics, and mass redistribution. The paleomagnetic record also captures the reversals. In the seafloor, alternating stripes of normal and reversed polarity extend outward from mid-ocean ridges in both directions, like a recording of the field's history printed in stone. The width of each stripe corresponds to how long the field spent in that polarity before reversing. The record is detailed enough to identify periods called geomagnetic excursions, brief events where the field weakened and began to shift, but then recovered without fully reversing. The Lachamp excursion, roughly 42,000 years ago, is the most studied of these. During that event, global field intensity dropped dramatically over several centuries, then recovered over several thousand years. Evidence in cave records, ice cores, and tree rings from that period suggests elevated cosmic ray flux during the excursion. Some researchers have connected it to periods of accelerated climate change and megafauna extinction, though the causal chain is debated. The point is not that another Lachamp is imminent. The point is that these events are real. They have happened. They left measurable signatures in the biological and geological record. And the current state of the magnetic field has measurable similarities to the early stages of past excursions. The ancient record does not predict the future, but it defines the range of what is possible. It shows what Earth has been through. And it shows that the extremes are more extreme than intuition suggests. The rocks also tell us something about the last time rotation behaved the way it is behaving now. What was happening on the surface during those periods was not calm. Determining the exact rotation rate of Earth at a specific point in the deep past is not a simple calculation. The records are incomplete. The proxy measurements have uncertainties. And the causes of past speed changes are not always identifiable from the evidence left behind. But researchers have assembled enough of a picture to say something meaningful about the trajectory. The last period in Earth's recent geological history, when rotation accelerated on a scale comparable to what is now being measured, was likely during the end of the last glacial maximum. The period, roughly 15,000 to 20,000 years ago, when the ice sheets that had covered large portions of the northern hemisphere began their final retreat. As those ice sheets collapsed, massive amounts of meltwater entered the ocean, redistributing planetary mass in ways we discussed earlier. The crust, freed from the weight of the ice, began to rebound upward in a process that is still continuing. The redistribution of mass affected the moment of inertia, and therefore the rotation rate. The parallel to the present is imperfect, but instructive. We are not in a glacial retreat. We are in a different kind of deglaciation, one driven not by orbital forcing, but by atmospheric warming. The timescale is faster. The geography of ice loss is different, but the physical mechanism is comparable. Mass that was at the poles is moving toward lower latitudes. The crust is adjusting, and the rotation is responding. What the geological record of the last glacial retreat tells us is that these mass redistribution events do not produce smooth, gradual changes in rotation. They produce irregular stepwise shifts as different ice sheets collapse in different sequences, as meltwater pulses occur in episodes, and as the solid Earth responds with its own delays and rebounds. There were periods during the last deglaciation where sea level rose by meters within centuries. Meltwater pulse 1A, roughly 14,500 years ago, raised global sea levels by roughly 14 to 18 meters in a span of roughly 300 to 500 years. The redistribution of that volume of water in that time frame was large enough to leave a detectable signature in rotation models. The volcanic record adds another dimension. During periods of rapid deglaciation, volcanic activity tends to increase. The mechanism is pressure release. Ice sheets exert enormous weight on the crust beneath them. When that weight is removed, the crustal pressure drops, and the mantle rock beneath, which was already near its melting point due to geothermal heat, becomes more likely to melt and rise. The result is increased volcanism in deglaciated regions. Iceland is one of the most studied examples of this effect. Research on Icelandic volcanic history shows elevated eruption rates during and after the last deglaciation, with a lag of centuries between ice removal and volcanic response as the crust adjusted. The same process is expected to operate during the current period of ice loss, and there is early evidence that it is beginning to do so. Monitoring in Iceland, Greenland's peripheral volcanic zones, and West Antarctica has shown subtle changes in subsurface pressure and seismic activity that are consistent with the start of a deglaciation-driven volcanic response. That response has its own timeline and its own potential to interact with the rotation system, as volcanic activity can distribute mass across the crust in ways that affect the moment of inertia. The picture that emerges from the geological record is not one of catastrophe on human timescales. It is one of interconnected changes, each driving the next, each adding to a cumulative shift that takes centuries to fully express. What concerns researchers watching the present data is not any single measurement. It is the number of systems changing simultaneously. And what happens when those signals are laid on top of each other is the most unsettling part of this entire story. The connection between faster rotation and earthquake and volcanic activity. In 2017, a paper published in Geophysical Research Letters made a claim that drew immediate attention from both scientists and the public. The researchers had analyzed historical earthquake data going back more than a century. They found that periods when Earth's rotation slowed slightly were followed roughly 5 years later by increases in the number of major earthquakes, those measuring magnitude 7 or above. The correlation was statistically significant, and the mechanism they proposed was physically grounded. When Earth's rotation slows, even fractionally, the equatorial bulge, the slight thickening of the planet at its middle caused by centrifugal effects, adjusts. The crust at lower latitudes shifts inward slightly as the rotation rate drops. That movement applies horizontal stress to tectonic plates. Faults that were already close to failure get nudged over their threshold. The same logic runs in reverse. When rotation speeds up, the equatorial bulge increases slightly. The crust at the equator stretches outward. Faults under tension, rather than compression, can be triggered. The type of earthquakes most likely to be influenced differs from the slowdown scenario, but the triggering mechanism is the same. Rotational change, applying stress to a crust already under pressure from tectonic forces. The paper noted that we had recently exited a period of slowing and entered one of acceleration. By their model, the mid-2020s would be a period to watch. That prediction has not been proven or disproven definitively. Earthquake prediction is one of the most difficult problems in Earth science, and most seismologists are cautious about strong claims. The correlation identified in the study is real, but correlation does not establish causation. And the mechanism, while physically plausible, has not been confirmed through independent modeling to the point where the scientific community considers it settled. What is less contested is the volcanic side of the equation. Rotation rate changes affect the behavior of fluids beneath the crust. The outer core is one such fluid, and its response to rotational changes is well documented. But the upper mantle also contains partially molten rock in certain regions, and changes in rotational stress can affect where and how that material moves. A study examining global volcanic eruption rates over the last 500 years found a weak but detectable correlation between periods of rotation anomaly and subsequent volcanic episodes. Again, with a lag of years to decades between the rotational signal and the surface response. The lag matters. It means that the effects of the current acceleration whatever they turn out to be at the surface, may not be fully expressed yet. This is the part of the story that researchers find genuinely difficult to communicate without either understating the science or veering into alarmism. The planet is under more simultaneous stress right now than at any point in the modern instrumental record. The rotation is anomalous. The core is behaving differently. The ice is redistributing. The magnetic field is weakening in a specific region. And the atmosphere itself, which has its own physical coupling to rotation, is shifting in ways that add to all of the above. None of these individually constitutes a crisis. Combined, they represent a set of forcing factors acting on the same geological system simultaneously, and the system's response to simultaneous forcing is less predictable than its response to any one of them in isolation. There is one more member of this list that has not been fully addressed yet. The atmosphere itself, the layer of gas wrapping the planet, weighing roughly 11 quadrillion pounds in total, moves constantly. And its movement is not just weather. It is a physical force acting directly on the rotation of everything beneath it. The atmosphere is not light. It does not float passively above the surface. It is a layer of gas with mass, and that mass moves. When it moves, it pushes. The total mass of Earth's atmosphere is roughly 5.1 quintillion kilograms. That is comparable in scale to the mass of large mountain ranges. When that mass redistributes itself, shifting from one latitude to another as weather systems develop and dissipate, it applies real, measurable torque to the rotating planet beneath it. This is not a theoretical coupling. It is measured directly. Meteorologists and geodesists have spent decades comparing atmospheric angular momentum data with Earth rotation data. The match is striking. When the atmosphere gains angular momentum, typically through the amplification of large-scale wind systems, the solid Earth slows down slightly to maintain the balance. When the atmosphere loses angular momentum, the solid Earth speeds up. The total angular momentum of the system stays constant, just redistributed between air and ground. The dominant signal in this exchange is seasonal. The winter hemisphere develops stronger west-to-east jet streams. Those jet streams carry angular momentum. The solid Earth responds by rotating slightly slower in the boreal winter than in the boreal summer. The effect is small but measurable at the precision of modern atomic clocks, on the order of 1 millisecond variation across the year. But there are non-seasonal components. El Niño events are the most significant. During a strong El Niño, trade winds weaken across the tropical Pacific. The atmosphere transfers angular momentum to the ocean, and the coupling from the ocean to the solid Earth produces a detectable change in rotation rate. Strong El Niño events in 1982 to 83, 1997 to 98, and 2015 to 2016. Each produced measurable rotation anomalies. The 2015 to 2016 El Niño was one of the strongest on record. It coincides closely with the beginning of the surface acceleration trend that researchers have been tracking. That timing is not necessarily causal. The acceleration has persisted well beyond the El Niño's influence, and the magnitude of the effect is larger than El Niño alone can explain. But El Niño may have contributed to the initial departure from baseline behavior that the core and ice dynamics then extended. Here is where it gets structurally important to the overall picture. The atmosphere is not just a passive passenger. It responds to changes in the ocean. It responds to changes in ice coverage and albedo. It responds to changes in the magnetic field through effects on ionospheric circulation. All of these connections mean that as other systems in this story change, the atmosphere changes too. And its rotational effect changes with it. A shifting jet stream pattern, which has been documented over the past 2 decades and is linked to Arctic warming, changes how atmospheric angular momentum distributes across latitudes. The stratospheric polar vortex, when it weakens and disrupts, spills cold air equatorward in a way that redistributes atmospheric mass and creates a brief but measurable rotational pulse. The atmosphere is not just a complicating factor in the rotation story. It is an integrating factor. It receives signals from ice loss, ocean warming, and core-driven magnetic changes, and it rebroadcasts them as mechanical forces on the crust below. Every year, the atmosphere changes. It changes its contribution to rotation, and the atmosphere is changing faster now than at any point in the modern record. But even with all of this, the atmosphere is not the only fluid system with a braking function on the planet. The oceans are doing something too, something quieter and in many ways more consequential for the long-term picture. If you have ever dragged your hand through water while moving quickly, you have felt ocean drag. The principle at planetary scale is the same. Earth's oceans cover more than 70% of the surface to an average depth of roughly 2.5 miles. They interact with the rotating solid Earth through friction and pressure at the ocean floor. That interaction creates a braking effect. It is small compared to tidal friction from the moon, but it is real, measurable, and changing. The ocean's angular momentum, like the atmosphere's, is tracked continuously. The two combine in what scientists call Earth's total angular momentum budget, the accounting system that tells us how rotation energy is being distributed among the solid Earth, the oceans, and the atmosphere at any given moment. When ocean currents strengthen, they carry more angular momentum, and the solid Earth slows fractionally. When they weaken, the solid Earth speeds up fractionally. The deep ocean circulation system, the network of currents driven by differences in water temperature and salinity that circulates water through all of the world's ocean basins over timescales of hundreds to thousands of years, is changing. The Atlantic meridional overturning circulation is the component of this system that carries warm surface water northward along the eastern coast of North America and toward Europe, then sinks as it cools and becomes denser, and returns southward as a deep cold current. It has been weakening. Multiple independent datasets, including sediment records, satellite altimetry, and direct current measurements, confirm that the circulation is operating more slowly than it was several decades ago. Some studies suggest it is now at its weakest point in at least 1,000 years. The rotational implication of a weakened circulation is not straightforward. The circulation transports angular momentum through the ocean basins in a specific pattern. When the pattern changes, the distribution of ocean angular momentum changes. Some components of the change would add to Earth's surface speed. Others would subtract. The net effect depends on the details of how the circulation reorganizes. What is clearer is the thermodynamic side. Warmer ocean water is less dense. A less dense ocean occupies more volume. Sea level rises, not just because ice melts, but because the water itself expands. And as the upper ocean warms and the deep ocean slowly follows, the vertical structure of the ocean changes. The boundary between warm surface water and cold deep water, called the thermocline, deepens. This changes where angular momentum resides within the ocean column, and therefore how it couples to the rotation. There is one more physical effect that connects warming oceans to rotation through a completely different pathway. Warmer ocean surface temperatures drive more intense and more frequent tropical storms. A major hurricane is a rotating atmospheric structure that contains significant angular momentum. The formation and decay of these storms redistributes angular momentum between the atmosphere and ocean in ways that carry a rotational signal. An ocean that generates more intense storms more frequently is an ocean that perturbs the rotation budget more often. The cumulative effect of all these ocean changes is not yet large enough to be the dominant driver of the surface acceleration, but it is real, it is measurable, and it is growing. And among the researchers watching all of this, there is a specific threshold, a boundary condition that would change the conversation entirely. Not a tipping point in a metaphorical sense, a literal tipping point in the mathematics of the rotation system. And some scientists believe we are not as far from it as we might hope. Not every researcher watching Earth's rotation data interprets the current acceleration as the beginning of something prolonged. There is a legitimate scientific position, held by a significant portion of the geodesy community, that the current speed-up is a transient phenomenon, a fluctuation near the top of its cycle that will be followed by a return to the long-term deceleration trend. The argument runs like this: Earth's rotation has always oscillated on multiple timescales simultaneously. There are decadal fluctuations driven by core-mantle angular momentum exchange. There are interannual fluctuations driven by atmospheric and ocean cycles. There are seasonal fluctuations tied to atmospheric mass redistribution. These oscillations are real, and they do not all move in the same direction at the same time. The current surface acceleration, on this interpretation, represents a phase of these overlapping cycles where several components happen to align in the speed-up direction simultaneously. The acceleration is unusual in its magnitude, but not necessarily in its nature. Given enough time, the cycles will move out of alignment, and some will begin pulling in the deceleration direction, eventually reversing the trend. Supporting this view is the geological record, which shows that similar speed-up episodes have occurred before and have always been followed by a return toward the mean. The counter-argument, made by a different group of researchers, is that the current situation is structurally different from past fluctuations in at least two ways. First, the drivers are not purely cyclical. Ice sheet loss is not an oscillation. It is a one-way trend that is accelerating. The mass redistribution it causes does not reverse when a cycle completes. It accumulates. Each year of ice loss adds to the cumulative shift in the planet's moment of inertia and the rotational effects of that accumulation compound. Second, the inner core's apparent behavioral change, if real and if ongoing, represents a structural shift in the system, not a phase of a cycle. A core that has changed its rotation direction is not simply a cycle in a different phase. It is operating in a different regime. And the coupling between that regime and the surface rotation is not well understood enough to confidently project its future trajectory. The honest answer, as of the current state of science, is that both groups have valid points, and neither has the data to definitively resolve the question. What can be said is that the range of possible future trajectories is wider than it was 20 years ago. The system is less predictable, not because our instruments are worse, but because the forcing conditions are further from any historical analog in the instrumental record. That widening of uncertainty has practical consequences. The systems that depend on Earth's rotation for calibration, the timekeeping infrastructure, the satellite navigation networks, the power grids, have built their safety margins around a planet behaving within a range established by decades of observation. If the planet moves outside that range in either direction, those margins become insufficient. And the engineers responsible for keeping those systems running have been quietly running the numbers. What they found is not reassuring. There is a number that appears in the technical literature on Earth, rotation and timekeeping infrastructure that most people outside the field have never encountered. 1 second. Not 1 second in the sense of a heartbeat, 1 second in the sense of the accumulated difference between atomic time and Earth time that would force a negative leap second, even after the policy decision to eliminate them takes effect in 2035. Here is the mechanism. The decision made by the international standards bodies was to allow atomic time and Earth time to diverge without correction, rather than applying potentially destabilizing leap seconds. But the agreement included a limit. The gap between the two timescales would be permitted to grow to a maximum of 1 minute before a different correction mechanism would be applied. 1 minute sounds large. At current rates, it would take roughly a century to accumulate, but current rates are not a reliable guide to future behavior. If the acceleration continues, the gap grows faster. If a reversal occurs and the planet slows dramatically, the gap grows even faster in the opposite direction. The tipping point is not the 1 minute limit. It is the rate at which the gap approaches that limit. Infrastructure systems plan on time scales of decades. Power grids, communications networks, and satellite constellations are designed with a design lifetime of 20 to 30 years. The systems being built today will still be operating in 2050. The engineers specifying those systems have to make assumptions about what the timekeeping environment will look like across that window. If the current acceleration continues for another decade and is then followed by a rapid deceleration, the gap between atomic and Earth time could grow faster than the policy limit assumes. Systems calibrated to a slow divergence rate would encounter a faster one. There is a separate tipping point in the physical system itself. Researchers studying the interaction between ice loss, sea level rise, and coastal geology have identified certain configurations where the feedback becomes self-reinforcing. As ice sheets lose mass, the land beneath them rebounds upward. That rebound changes the gradient of the ice sheet surface, affecting how meltwater drains in some regions. A specific threshold of ice loss triggers a drainage reorganization that accelerates further loss, independent of whatever caused the initial melting. This is the kind of tipping point that is, by definition, difficult to detect before you have crossed it. The rotation connection is that meltwater pulse events, rapid, large-scale influxes of meltwater into the ocean over decades rather than centuries, produce rotation signals that are both large and abrupt. The existing correction infrastructure was not designed for abrupt signals, and there is one more threshold that appears in the literature on core dynamics. Researchers modeling the behavior of the outer core under different boundary conditions have identified flow patterns that can shift between two stable states. Much the way a bistable system in physics can sit in either of two equilibrium configurations. The current flow pattern, which appears to be associated with the surface acceleration, may represent one such state. If the system transitions to the other state, the surface effect could reverse rapidly. A planet that has been accelerating could begin decelerating sharply, producing a gap accumulation rate that current infrastructure would struggle to compensate for. Whether we are near any of these thresholds is genuinely unknown, but the systems that would be affected by crossing them are already showing the early signs of strain. The phrase, Earth's rotation affecting daily life, sounds abstract. It sounds like something that matters to physicists and not to anyone else. Here is why that assumption is wrong. Every commercial aircraft flying today navigates using a combination of satellite positioning, inertial reference systems, and radio navigation aids. All of these systems are synchronized to coordinated universal time. When a flight departs from one continent and arrives at another, the navigation computers have been tracking position continuously against a model of Earth's orientation in space. Any inaccuracy in that model propagates directly into position error. Modern aircraft use GPS-based approach, procedures that are approved for use in visibility conditions where the pilots cannot see the runway until they are roughly 100 feet above it. The tolerances on these approaches are measured in meters laterally and feet vertically. The systems delivering that precision are the same systems that depend on Earth, rotating predictably. Aviation safety authorities have already issued technical bulletins acknowledging that increasing anomalies in Earth's geomagnetic and rotational behavior require more frequent updates to navigation databases. The update cycle for aviation navigation data has historically been 28 days. Some categories of data are now being flagged for more frequent review. Power grids operate on alternating current at a fixed frequency, 50 or 60 cycles per second, depending on the country. Grid operators use time synchronization to coordinate the phase of current across interconnected systems spanning thousands of miles. When two sections of a grid run slightly out of phase with each other, energy does not transfer efficiently across the connection. When the phase mismatch grows beyond certain limits, automatic protective systems disconnect the sections to prevent equipment damage. Those protective systems are calibrated to thresholds established by decades of operating experience under conditions where timekeeping was stable. Unusual timekeeping conditions, even subtle ones, can produce phase behaviors that fall outside the calibration range. Grid operators in Europe and North America have both published technical analyses of how timekeeping anomalies propagate into grid behavior. The conclusion in both cases was that existing protective systems are adequate for the current level of anomaly, but would require recalibration if the anomaly grew significantly. The hospital system is perhaps the least obvious example and possibly the most serious. Modern hospitals are dense with time-critical systems. Medication dispensing systems log timestamps on every dose. Operating room equipment, particularly anesthesia delivery systems and patient monitoring, records data against synchronized timestamps that form the legal medical record. Radiological equipment, especially linear accelerators used in cancer treatment, uses precise timing to coordinate beam delivery with patient breathing cycles. In each of these applications, a 1-second discontinuity in the timekeeping system does not just create a data anomaly. It creates a gap in the medical record that triggers automatic safety alerts and, in some cases, automatic system shutdowns, pending manual verification. Hospital information technology teams have been aware of the leap-second problem since at least the 2012 crash that affected multiple technology platforms. Most have implemented mitigations, but mitigation is not elimination. The deeper issue is not that these systems will fail catastrophically overnight. It is that they are being maintained by teams that are spending increasing resources managing an environment that was supposed to be stable. Resources spent maintaining timekeeping stability are resources not spent on other improvements. And as the underlying planet behaves more unusually, the maintenance burden grows. There is a broader picture that most of these individual engineering teams do not have full visibility into. What happens when you lay every one of the signals described in this video on top of each other and look at the aggregate pattern? It does not look like noise. Here is what makes the current situation different from anything in the modern record. It's not that one thing is changing. It's that everything is changing at once. When a single system experiences pressure, scientists can model it, predict it, understand what comes next based on decades of observations. One force pushing on one system follows rules that are well established. But Earth right now isn't experiencing one change. It's experiencing 7, 8, maybe 10 simultaneous changes across systems that normally move independently. And those systems aren't just changing. They're connected to each other through feedback loops that amplify the changes in ways the models weren't built to predict. The rotation is anomalous, accelerating beyond any measurement in the modern record. The inner core has shifted its rotational behavior. The outer core circulation pattern has changed, producing both a rotation signal and a magnetic field signal. The magnetic field has weakened regionally and globally, with a specific anomaly expanding over a populated continent. The ice sheets are losing mass at rates that were not projected to occur until later in this century, under median climate models. The meltwater redistribution is shifting the planet's axis and altering its moment of inertia. The oceans are warming, expanding, and changing their circulation. The atmosphere is responding to all of the above and feeding its own angular momentum changes back into the rotation. And the geological indicators, the seismic patterns, the subsurface pressure changes in deglaciated regions point toward a slow-building, volcanic and tectonic response that is only beginning. Each of these is documented. Each has its own research literature. Each is being monitored by separate scientific communities with separate funding streams and separate publication venues. What is less common is the attempt to look at all of them together. When researchers have done that, what they find is that the changes are not independent. They are coupled. The weakening magnetic field reflects outer core changes that also affect rotation. The ice loss affects both the rotation and the ocean circulation, which affects the magnetic field's excitation pattern. The atmospheric shifts affect rotation and also affect where precipitation falls, which affects ice accumulation rates. These are not metaphorical connections. They are physical couplings with measurable signatures. The result is a system that is moving in multiple directions at once, where each change pushes on the others, amplifying them in ways that compound faster than any single change would on its own. Scientists have a term for what happens when a system's fundamental behavior starts changing. They call it non-stationary, which sounds technical but means something simple and unsettling. The rules that governed how Earth behaved for the last 10,000 years are shifting. The average is moving. The range of variation is widening. The patterns that held steady long enough for civilization to develop around them are no longer holding steady. And the historical record, the data we've relied on to predict what comes next, is becoming less useful because the planet is moving into conditions it hasn't experienced in thousands of years. This is not a cause for panic. Science has dealt with changing systems before and adapted. Monitoring networks are being expanded. Models are being revised to account for the new conditions. The scientific community is aware of what's happening and working to understand it better. But it is a cause for honesty about how much we don't yet know and how wide the range of possible outcomes has become. The last major period in Earth's history where this number of systems changed simultaneously left a record in the rocks and sediments that researchers have been reading for decades. What that record shows about the scale of possible change is something that most public discussions of any individual component do not fully convey. And there is one measurement, one aggregate picture produced by mapping all of the above signals together, that stops researchers mid-sentence when they see it for the first time. In research institutions studying Earth's geophysical behavior, there is a type of visualization that has become increasingly common in the past 5 years. It takes the independently measured datasets from each of the systems described in this video, normalizes them to a common scale, and plots them on the same timeline. The result is something researchers refer to privately as the alignment. Core rotation anomaly data, referenced against the 1990s baseline, shows a clear departure beginning around 2009 to 2010. The departure strengthens through the mid-2010s. Outer core angular momentum estimates, derived from magnetic field change rates, show a concurrent shift beginning in roughly the same window, with a slightly different profile that reflects the different coupling timescale between inner and outer core. Surface rotation data shows the acceleration beginning to emerge, clearly from background noise, around 2016, with the most extreme values appearing in 2020 through 2022. Greenland ice mass loss rate, plotted against its pre-2000 baseline, shows a step change increase beginning around 2012 and continuing to steepen. South Atlantic anomaly, minimum field intensity, tracked since satellite measurements became available, shows a consistent decline with a steeper gradient emerging in the mid-2010s. Arctic sea ice extent, used as a proxy for the atmospheric circulation changes affecting jet stream behavior, shows its sharpest multi-year decline beginning around 2012. Atlantic meridional overturning circulation, strength estimates, derived from ocean heat transport proxies and direct measurements, show accelerating weakening in the mid-2010s. Each of these time series, measured independently by different instruments, different institutions, and different scientific communities, shows its major departure from the historical baseline in roughly the same decadal-long window, centered on approximately 2010 to 2020. This is not a constructed narrative. It is what the data shows. The probability that 7 independent geophysical systems all departed from their historical baselines within the same decade, by coincidence, with no shared physical driver, is not zero, but is very small. What it suggests is that these systems share a common excitation. Something changed in the coupled Earth system during that window in a way that propagated across multiple layers simultaneously. Whether that something was primarily the inner core, primarily the ice atmosphere system, or primarily the magnetic transition, the effect was system-wide. And system-wide changes in Earth's coupled geophysical behavior do not stabilize quickly. The geological record shows that when multiple systems enter a departure phase together, they tend to remain in that departure for decades to centuries before returning to a new equilibrium. And the equilibrium they find at the end is not identical to the one they left. That is the most important sentence in this video. The equilibrium they find at the end is not identical to the one they left. The planet is not broken. It is not dying. Life has survived far more extreme transitions than this one, across hundreds of millions of years of far more dramatic geophysical events. But the infrastructure of human civilization was not built to operate across a geophysical transition. It was built to operate in a stable period, by the standards of geological time, of extraordinary calm. And what comes next is the question that has no clean answer. Everything described in this video is confirmed science. The measurements are real. The instruments are calibrated. The data has been reviewed, challenged, replicated, and published. Earth is rotating faster than it has in 50 years of precise measurement. The inner core has changed its behavior. The outer core's circulation has shifted. The magnetic field is weakening. The ice sheets are losing mass faster than projected. The ocean's circulation is weakening. The atmosphere is responding. The rotation axis has moved. The combined signals line up in a way that points to a shared origin. All of that is established. What comes next is the part science cannot yet answer with confidence, and it is the part that matters most. Human civilization was built during one of the most geodynamically stable periods of the last several 100 million years. The 10,000 years since the end of the last glaciation were unusually quiet by geological standards. Rotation varied within a narrow band. The magnetic field was relatively stable. The ice sheets retreated at a manageable pace. Sea levels rose gradually and then stabilized. In that stability, we built cities at coastal elevations that assumed sea level would not change rapidly. We built satellite infrastructure that assumed Earth would rotate predictably. We built power grids and financial systems and hospital networks that assumed the clock would run smoothly. We built navigation systems that assumed the poles would not move. Every one of those assumptions is now being tested. Not catastrophically, not all at once, but consistently, and in a direction that creates increasing pressure on systems built for a different planet. The question that the scientific community is working hardest to answer right now is not whether these changes are happening. They are. It is not whether they are connected. They appear to be. The question is how fast the transition will proceed and whether the coupled feedbacks will stabilize at a new equilibrium within the next few decades or continue accelerating. The difference between those two scenarios is enormous for every decision being made right now about infrastructure policy and resource allocation. If the system stabilizes within a generation, the engineering problems are manageable. The corrections needed are large but finite. The institutions that maintain global infrastructure have enough time to adapt. If the feedbacks continue to amplify, the window for managed adaptation narrows. The corrections needed grow faster than institutions can implement them. The systems with the least redundancy fail first, and their failures stress the systems connected to them. Neither outcome is certain. And the honest answer from the researchers closest to the data is that the uncertainty is larger than it was a decade ago, not smaller. More monitoring has produced more evidence of change. Better models have produced better resolution of the mechanisms, and better resolution has revealed how tightly coupled the systems are, which means how much a change in one can drive changes in others. The planet you live on is not static. It never was. It breathes, moves, shifts, and changes across timescales that dwarf recorded history. What is happening now is not outside the range of what Earth does, but it is outside the range of what Earth has done during the time humans have been here. And the one question that science still cannot answer, the one that sits at the center of every model, every dataset, every late-night discussion in geodesy departments and geophysics laboratories, is simple. How fast? How fast are we moving toward the new equilibrium? That answer is being written right now in the rotation of a planet you are standing on, in the movement of ice you cannot see, in the churning of iron 2,900 miles below your feet. The instruments are running. The data is coming in. We are watching in real time. Thanks for staying with me through this journey into one of the strangest things happening to Earth right now. The planet beneath your feet is changing in ways that most people will never notice. But that doesn't make those changes any less real or any less important. If you found this exploration meaningful, please consider liking this video and subscribing to the channel. Your support helps me continue making these deep explorations of the world we live on and our place in it. Sleep well tonight, knowing that you're standing on a planet that's been through far stranger things than this, and that the systems watching over it are among the most sophisticated humanity has ever built.